Stanford University.
All right, so last quarter we studied classical mechanics, and classical mechanics is fairly intuitive. The basic ideas are things that you can visualize. You can picture in your head motion of particles, motion of objects. It gets a little hard when you start thinking of 10 particles all at the same time, but nevertheless, the whole thing is based on concepts that are drawn from pretty much the everyday world. Of course, it gets more and more abstract as you go along. The crazy French, who were obsessed with elegance, kept making it more and more and more mathematically elegant. Lagrangians, Poisson brackets, blah, 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 turned out all to be tremendously important. The abstractions, though, are not all that difficult to understand. And the basic concept is the concept of updating. Well, before that, the concept of a space of states. What is a state of a system? Well, even before that, the concept of a system. A closed, isolated system that doesn't interact with anything and whose motion and whose evolution, whose history you wish to predict. Classical mechanics is predictive. It's deterministic. And the first concept, as I said, after the concept of a system, is the concept of the state of a system. Systems can have a collection of different states. We talked about some very simple examples the first day of the quarter last time. I just described for you the most elementary simple systems consisting of nothing more, for example, than a coin, heads and tails. The only states of the system are heads and tails. They form a mathematical set, the states. Two of them for heads and tails, 2 points, one space, 2 states. And we can draw them as dots. This one stands for heads, this one stands for tails. And, you know, it's easy to picture in your head. From there, we talked about equations of motion. Equations of motion or laws of evolution. For the simple, very simple system of a couple of points, heads, tails, we formulated some very, very simple possible laws of motion. The simplest being nothing happens. If you start with heads, you stay heads, 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 heads. If you start with tails, you stay tails, 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 tails. That was a very simple law of motion. A more complicated law of motion, if you begin with heads, you go to tails. If you begin with tails, you go to heads. And just oscillate back and forth. The basic idea is the idea of updating. If you know everything there is to know about a system at an instant of time, then classical mechanics, everything that there is to know essentially means everything that's needed in order to predict the future. If you know everything that needs to be known, then classical mechanics consists of a set of equations which tells you how to update the state given its value at any given time, how to go from one time to the next. That basic idea, for example, well, I don't think I need to describe the examples again. We described them at length last time. And that's extremely intuitive. In going from these very simple discrete examples to a world of continuous motion, indeed we have to abstract. We have to replace the idea of a small number of states, a small finite number of configurations, by an infinite number of configurations. For example, the motion of a particle along a line, we have to label the states by the points along a line as well as their velocities. And so it does get more complicated, but nevertheless, Classical physics consists of equations which tell you how to update the state at any given time, and it's completely deterministic. And as I said, easy to visualize, or at least by comparison easy to visualize, because it makes use of concepts from the ordinary world which your brain is rather hardwired to be able to understand. Now, I always give a little sermon at this point, and I'm going to give it again. Probably you've heard it a dozen times, about the way one has to think about physics beyond classical physics, when you move past classical physics. I don't think it can be said enough, and it's so rarely said that I think I will say it again. And it's that once physics moves past the realm of parameters that has to do with ordinary experience, either objects which are so small that they're far beyond what ordinary physics is about, or velocities which are so fast that they're far beyond ordinary velocities, whenever we move out of the range of parameters that we're familiar with from ordinary experience, we inevitably run into things that we cannot visualize. Nobody can visualize the motion of an electron. You're just not wired for it. Nobody can visualize four-dimensional space or four-dimensional space-time, let alone 10 or 11 dimensions. It's not the way physics is done. I often read some of the stuff that goes back and forth between some people, I suspect people in this class, about trying to explain to themselves, to each others, or to ask questions of each other about certain abstract physical questions. And I notice very much that a lot of the mistakes, a lot of the confusion happens because of trying to visualize things using the old-fashioned or standard intuitions that you're hardwired for. You may think that physicists, good physicists, are especially good at visualizing these things. They're not. I cannot visualize 5, 6, 7 dimensions any better than you can. But I know how to use abstract mathematics to describe it. There's no substitute. There really is no substitute for the process of abstracting and using mathematics to describe the things which are beyond your ability to directly visualize. The example that I always give, and I'm going to do it again tonight, I just want you to really focus on it and realize that you're not going to understand quantum mechanics by trying to visualize it as some funny form of classical mechanics. It won't work. You'll always get it wrong. But just the idea of visualizing space of dimensions different than 3 dimensions. In particular, I always used to say, okay, how many people here can visualize 5 dimensions? And everybody would say, no, we can't. Of course, there was a few fakers, a few clowns in the class who would say, yeah, I can do it, but they couldn't, and they know they couldn't. They can't visualize 5 dimensions. But then I began to realize also, you probably heard this before, that it's equally hard to directly visualize 2 dimensions. And so I would say to the class, okay, how many people now can visualize 2 dimensions? And almost everybody would raise their hands. And I would say, no, you're wrong. Close your eyes, try to visualize 2 dimensions. And they would. They say, okay, I see it. I see 2-dimensional curved space. What they're seeing is not 2-dimensional curved space. What they're seeing is a 2-dimensional surface embedded in 3 dimensions. Even try to see 1-dimensional space. 1-dimensional, abstract 1-dimensional space is just a line. You cannot see that line in your head without seeing it as a line drawn in a plane, and the plane you can't see without seeing it as embedded in 3 dimensions. What's going on? Why can't you? I hate to tell you this, but you're prisoners of your own neural architecture. Your neural architecture was built for 3 dimensions. All right, how do you get around it? Well, you don't get around it by training yourself to see 4, 5, 6 dimensions. You get around it by training yourself to think abstractly about it. Okay? If three-dimensional space is a point x, y, and z, then four-dimensional space is x, y, z, and w. And you learn to manipulate the symbols. Now, that's not to say that after a while you don't start to gain a new kind of intuition for things. You do. But the intuition is not the process of physical visualization of the same kind as when you visualize a wave as a wave in the ocean. So I warn you about that. And I will tell you, quantum mechanics is about as abstract as anything can be. Well, perhaps things are even getting a little more abstract now. But again, quantum mechanics is about things that your evolutionarily developed neural structure is not prepared to deal with directly. Now, how do you deal with it? Abstract mathematics again. And relativity, it's also true of relativity. It's worse in quantum mechanics. Okay, let's begin with quantum mechanics at the very, very simplest, most primitive question you can ask. What is the state? Well, I think we can ask the most primitive question is, what is a system? Now, I don't think I can answer it. It's a sort of undefinable. You start with the idea of a system, and I don't think I will try to give it a definition. But in particular, a closed system is one which, at least temporarily, is not in interaction with anything else. It's isolated. It is not interacting with anything else. And so it can be described by itself as a lonesome entity with nothing else involved. In classical mechanics, or it's not even a question of classical mechanics. It's a question of classical logic. The whole logic of quantum mechanics is different than the logic of classical mechanics. The logic of classical mechanics, again, begins, of course, with a system, which I won't try to describe, but the next step is the space of states, the collection of possible states of a system. If the system is a discrete system like a coin or a die, you know, the six-faced die, it can have 6 states. Of course, a real die, a real genuine die in three-dimensional space, of course, can be in all sorts of orientations. It has infinitely many states. But what I mean by a die now is I mean an abstract mathematical die whose states just consist of one of 6 numbers. Okay? The space of states is a set. 1, 2, 3, 4, 5, 6. This is the space of state of a die. This is the space of states of a coin. Now, again, an abstract coin which only has 2 states, heads or tails. This would be heads, this would be tails. The abstract space of a point particle moving along a line, what is that? Anybody know what that is? What's the abstract space of a particle moving along a line? Well, I'll remind you that the term is phase space. The space consists of the set of possible positions of the particles and the possible momenta, the possible velocities. And so, for a particle moving on a line, the possible states of the system form a plane, and the plane has a position, sometimes called Q, a momentum, sometimes called P, and every point on that plane is a possible state of the point particle moving along the line. But it's a set. In this case, it's a continuously infinite set of 2 dimensions, In this case, it just consists of 2 points. In this case, it consists of 6 points. And we can now start building some logical concepts for classical physics. For example, concepts such as or and and. What do they mean? Or and and are concepts which apply to collections of states. Let's consider a proposition, proposition such and such. The proposition could be that the die is has a value which is even valued. Okay? That's a subset of the space of states. In fact, it consists of 3 of them, if I'm not mistaken. 3 odd, 1, 3, and 5, yes. And another proposition would be the die is odd. No, did I say odd? I think odd, even, whatever the other possibility is. That's another non-overlapping set of configurations. Let's take another case. Let's take 2 propositions, one of which again is that the die is odd, and the other proposition is that the die is less than or equal to 3. All right, so let's see. Here's 1, 3, 5. Here's 2, 4, 6. And less than or equal to 3 is this set over here. So now they're overlapping sets, and we can ask for concepts like and or. For example, the proposition that the die is both less than or equal to 3 and odd is the intersection of these 2 subsets. 1 and 3 is odd and less than or equal to 3. So there's a concept of and that's in this subset and in this subset. The mathematical concept is the intersection of 2 sets. Is the intersection of 2 sets, or the sets which satisfies both things, and that's the concept of and. Given 2 propositions, each proposition is a collection of states. The concept of and is intersection. What about the concept of or? Or becomes the concept of union. What set of states here either is less than or equal to 3 or odd? It's the inclusive or, incidentally. Inclusive or means it can be both. All right? That's not the intersection of the 2 sets. It's the union of the 2 sets. The union meaning everything in both sets. Everything in here is either less than or equal to 3, or it is odd, inclusively, with both being allowed. So the inclusive or translates into the union, and the concept of and is the intersection of sets. That's the logic of classical reasoning to a large extent. Here's a concept. 2 sets are completely non-overlapping, this one and that one. That simply means the and statement is false. There are no states in there for which both things are true. Well, so there's a whole logic that is connected with the space of states being a set. And it's the logic of set theory. We're not going to do the logic of set theory, but it's important for me to tell you right now that the logic of quantum mechanics is different. It is not based on the idea that the state of a system is a set. The state of a system is something entirely different, and only in certain limits where systems behave classically, does whatever a space of states of quantum mechanics, whatever it is, does it approximately reduce to the concept of a mathematical set. In fact, just to tell you what it is, it's a vector space. And we'll talk about that. All right, but before we start to talk about the abstract mathematics of vector spaces and spaces of states of quantum systems, let's talk about experiments and describe the simplest possible system in quantum mechanics. It's the coin of quantum mechanics, the system with two states, heads and tails. We have to completely erase the blackboard and start over again. So we have some system, and whenever we measure that system, whenever we measure something or other about that system, namely the analog of whether it's heads or tails, we either get heads or tails. All right, let's give that a mathematical notation. I'm not going to call it a coin. I'm going to call it a qubit. A qubit is a system which can have two states, and Q stands for quantum. The analog for classical physics is called a C-bit, classical bit, and it is simply the idea of a coin, heads or tails. We're going to see that a qubit is a much more interesting, well, complicated for sure, but a much richer idea, even though it only has, in some sense, two states. Okay, so the qubit. The qubit, when it's measured, we're going to talk about measuring in a moment, is either heads or tails. But let's describe it another way. Let's give it a degree of freedom, a mathematical degree of freedom, and I'm going to call that mathematical degree of freedom sigma. Sigma is a traditional name for the degree of freedom describing a qubit, and sigma can either take on the value 1 or it can take on the value -1. It's 1 when the qubit is heads, and it's -1 when the qubit is tails. And there's no more content in it other than heads and tails, but it allows us to start being able to write equations for something. We can also describe this another way, by a picture. I'm going to describe sigma equals 1 by an arrow pointing up, and sigma equals -1 by an arrow pointing down. No implication here of anything geometric for the moment, just a notation. A notation, three different notations, heads or tails, sigma equals 1 or sigma equals -1, and arrow pointing up and arrow pointing down. Okay, now let's imagine an experiment. An experiment involves more than just a system. It involves a second system, and the second system is called the apparatus. In classical mechanics, we never bother thinking too much about the details, unless we happen to be experimental physicists and really going to go into the laboratory and do an experiment. We sort of don't worry very much about, at least in a deep sense. We think the system can be described completely without ever worrying about how you detect it, how you measure it, or anything else. But in quantum mechanics, one cannot get away ignoring the concept of an apparatus. So let's introduce an apparatus. And I'll tell you what we're going to make a mathematically abstract apparatus. I'm not going to tell you how it works. It's a black box. It's a black box. We're going to call it A. A for apparatus. It's a box and it has a little window. Here's the window. It also, it really is a box. It's like a carton. It's like the carton you get in the mail which says, this side up. This side up. You want it to stand upright. Okay. Here's a little window. By a window, I mean a little screen. And numbers appear on that screen. And it has some sort of detector on the end of a wire that, senses the qubit. and it senses whether the qubit is +1 or -1. So you start with your qubit, and you don't know what state it's in. The experiment is to determine what state it's in. So the qubit begins in the unknown, not the unknown state, but unknown. We don't know whether it's 1 or -1. And we're going to do an experiment. The experiment, as I said, I'm not going to tell you how the detector works. It's not important for us. It's only important that detectors do exist. And we will talk later about the process of detection, but not for now. So it has a sensor over here. Bring the sensor over to the qubit, and what does it do? A number lights up in here, either +1. Oh, first of all, let's start. Before we do the detection, the apparatus is in the neutral state, the blank state. No number there at all. So let's just call that the blank configuration of the apparatus. We take the apparatus over close enough to the qubit to interact with it, and if it's a good, faithful apparatus, it will then register a number here, and that number will either be +1 or -1. +1 or -1, depending on which way, whether it was heads or tails. That's the act of measurement. Now, you may or may not be there to look at the apparatus. This is a secondary. The apparatus has detected and recorded what has gone on here. So that's something that in classical mechanics, of course, we do the same thing. There's nothing particularly quantum mechanical about this, but we tend never to think about it in formulating the basic principles of quantum mechanics, classical mechanics. Okay, so that's an experiment that measures the state of, or it measures whether sigma is +1 or -1. But we can also think of it as another way. We can think of it not so much as a measurement, but as a preparation of the system. Here's the idea. Supposing we in fact do measure sigma to be +1. Supposing that's the outcome of the experiment, then we can erase the one that it wasn't and start over, and then say let's back off, reset the apparatus. Reset it means start it over in the blank state, and then redo the experiment again. Let's say we do it fast enough so that there wasn't much time for anything else to happen. What happens? What happens is that the detector records again, and if it's a good detector and the system hasn't had a chance to change very much, it will simply record the same number again. It will confirm the previous experiment. This is important, that experiments can be confirmed. Again, no difference between classical and quantum mechanics in this respect. We just emphasize it in quantum mechanics. Experiments can be confirmed. We can then do it again and again and again and again, and we will continue to get the same answer that we got in the first place. So one can say it a little bit differently. The first experiment, instead of saying that it determined whether it was heads or tails, we can say it prepared it in a state, which was in this case heads. After the first detection, it's now known to be heads. It has been prepared in the state heads. We can do the experiment over and over and over again and always get the same answer. All right, so a device that measures is also a device that prepares a system in a given state. Of course, the same thing would be true had the device determined in the first round that sigma was -1, then it would continue to detect the same thing. Of course, there can be bad detectors. Not all detectors are well made, and not all detectors work the way you want them to work, in which case it just wasn't a good detector. It didn't do what you wanted it to do.
What does heads and tails have to do with anything at this point? What's the purpose of having a heads and a tails?
There's just two possibilities. You want to know what it actually has to do with the head and the tail? There's just two possibilities. I just use that for familiarity. Doesn't have anything to do with heads and tails. Okay, now we're going to do something new. We're going to do a new experiment. First, we're going to start with a preparation. The preparation determined that the spin was, or a spin, I call it a spin. I'm giving away, it is a spin. The qubit is in the state +1. All right? So the qubit in the other notation is an arrow pointing up. We've prepared it. We now know, we can do it a few times to check. But once we check it, we now know that this qubit is up, and if we continue to do it, we will continue to get the same answer. But now we're going to do something funny. After we've determined or prepared the qubit, we're now going to take the detector and turn it over. I don't know. This side up. We've turned the detector over. And now we're going to probe the qubit again. And what do we learn in this case? We discover that instead of getting +1, we get -1. By turning the detector over, we get the opposite answer. What is this telling us? What is this telling us about the nature of this system? What it's telling us, oh, and of course then if we take our upside down detector and continue to do the experiment over and over, we'll continue to get -1. Of course, what happens if after we do it 35 times we turn the detector back upright? Then we get +1. What we are learning is that whatever this system is, this particular qubit has a sense of directionality to it. That when I drew it as up versus down, there really was a sense in which orientation is being distinguished. By turning the detector upside down, I interchange up and down. Well, that's what I normally mean by up and down. Turn it over, look at it upside down, and it changes the sign of the qubit. That's an indication that the qubit has some directionality in space, spatial directionality associated with it. Now, not all qubits do have spatial directionality associated with them. But by doing this experiment, we discovered that whatever this qubit is, it really does have a sense of orientation, an upness and a downness to it in space. So that's a piece of interesting information. We might begin to suspect that it's a vector. We might begin to suspect that since it has a directionality in space, it's a vector. When it's pointing up, it's different than when it's pointing down. We can make, well, yes. All right, so that's the basic idea of a qubit which also happens to have a sense of directionality. It's like this pin, and our detector, when we measure it, either measures it up or measures it down. But now we're going to do something else. Oh, here's what we might believe. Here's what we might believe. Given that the detector has an orientation to it, and it does have an orientation to it, there's a right side up and a wrong side up. In fact, in the detector, we might even think that there's something which is itself an orientation, something built into the detector which has an orientation in it. And you know what we might think? We might think that this detector is detecting the value of the component of a vector along the direction of the detector itself. So when the detector is right side up and it detects this thing here, it's detecting the component of some vector in the plus direction. When you turn the detector over, it's measuring the component of the same object except with respect to an axis which has been flipped. So you might start to think this thing is a vector, this qubit. Okay? So now we do something, say, all right, let's do something else now. Let's turn the detector on its side. Let's turn the detector on its side. We have initially determined that the qubit was up. We've definitely made sure it's up. We've done it 1,000 times with the right side up detector, and we know for sure it's up. It's not down. Yeah. And now we take the sideways detector. This side up over here, with its internal arrow pointing in this direction over here. And what should we expect ordinarily? Ordinarily, we would say, well, if this thing is going to measure now not the vertical component of some vector, but the horizontal component of some vector, we know that that vector was pointing upward by the initial preparation. What should you get here? Well, what's the component of this vector along the horizontal axis? 0. So the answer is we should get 0. If this were classical physics and this were a classical little vector, that's exactly what we would get. So we go and do the experiment, probe it, and we get not 0, but either 1 or minus 1 again. Which one do we get, 1 or minus 1? 1 and minus 1 sort of seem to be symmetrically located relative to the axis of the detector. So I say, oh, I got 1. Let's do this experiment a whole bunch of times. Let's go back. Let's go back. Get us a new qubit. Throw this qubit away. We're finished with it. Get us a new qubit. Make sure that it's pointing up, and do the same experiment again. Well, we might get plus 1 again. But again, we might get minus 1. We do it many, many times, exactly the same experiment, with the qubit known to be pointing up, and we measure what we would have liked to think was the horizontal component of it, and we always get plus 1 or minus 1. Randomly. Randomly, but in such a way that if you do it a great many times, then the average value is 0. As many plus 1s as minus 1s. So you do it a great many times, and you find every single one of them is either plus 1 or minus 1, but on the average it adds up to 0.
You said you threw the qubit away. What if you kept the qubit and looked at it again?
Well, if you reoriented it and made sure it was up again, then it wouldn't matter whether it was a new qubit or not.
If you look at the same qubit with the sideways and you look at it.
Okay, so good. Good question. All right, good. So let's go back. Good question. We started with a qubit known to be up. We made a detection and we got plus 1. The implication of that is the qubit is lying in the horizontal direction. Somehow we've detected a plus 1, but a plus 1 relative to a new axis. Not the original axis, but a new axis. Supposing we now take that same qubit, don't modify it, but do the same experiment over and over and over again. We will always get the same plus 1. Once that qubit has registered plus 1, and we don't disturb it, do the experiment again and again, we will continue to get plus 1. In other words, we will confirm the experiment.
Yeah. The difference between the two actions that you projected from going from top side to bottom side, that's 180 degrees flip, whereas the other is only a 90-degree flip.
That's right. That's right. When I turn the detector by 90 degrees, I no longer have definiteness about the answer. The answer is random, but only the first time. Once I do it, and I determine whether the horizontal component is +1 or -1, then it's determined, and if I do the same horizontal experiment over and over again, I will continue to get the same answer. Okay? Well, then I could come back and say, okay, now having done that and been pretty sure that the horizontal component of it is in the plus direction, I can come back and turn my detector again. Guess what will happen? I will find a random result. Half the times plus, half the times minus. But again, once it's determined and I do it over and over and over again, it stays the same. Yeah.
This is probably not important, but on your sideways detector, your arrows are, I think, going the wrong way.
How so?
They point from A.
Maybe this was an A here.
Yeah.
This side up, I think.
Okay. All right.
Yes, you're right. You're right. Yes. That's interesting, okay. So therefore, after having done this experiment and found out that I get a +1, I do it over and over and over a few times, I get a +1 each time. Let's say then I take the detector and turn it around by 180 degrees. What do I get? -1. But what happens if I only turn it by 90 degrees? Random. But what random means, a particular kind of randomness, equal probability for up and down. All right? Equal probability for +1 or -1. And that means that if I were to do the same experiment, the whole thing over and over, perhaps with a whole bunch of different qubits. I have a whole reservoir of qubits over here, lots of them. I don't even know what direction they're in, whatever they're doing. And I take them one at a time, I subject them to the first experiment. If I get up, I keep them. If I get down, I throw them in the trash. At the end of the day, what I've gotten myself is a whole bunch of qubits known to be pointing up. Now I take one of them and subject it to the sideways experiment. I may get 1, or I may get -1. I record what I got. Throw it away. Go to the next one. Do the same experiment. I may get +1, -1. Record what I get. Take this whole collection, large collection of them, and do the sideways experiment for all of them. What will be the average result?
50%.
0.
50%.
0. I will have as many +1s as -1s, and so the average will be 0. Let's write that, in this case here, by saying that the average value, we need a symbol for the average value, but after this experiment here, we will discover that the average value of the x, of the horizontal component of the qubit here, is 0. Classically, if we would have created a little vector in the up direction and we measure the horizontal component, we simply get 0. In the real world of quantum mechanics, we always get +or -1, but in such a way that the average is 0.
Is that true even if you don't throw away the ones that were measured to be -1?
Yeah, actually, it's still true. Yeah, that's correct. Yeah, yeah. The answer is yes. Yeah.
In your description, either the detector or the qubit seems to have some type of memory to it.
Some type of. Yeah, that's right. We're assuming that that the law of motion of the qubit is that nothing happens to it, so it remembers when you detect it, and then you detect it again instantly after, it hasn't changed. Right, that's correct. Right. Now, later on, we're going to consider possibilities where during the intervening time between measurements, some interesting thing may happen. But at the moment, we're supposing nothing interesting happens in between. It's the analog of the classical coin whose law of physics was just nothing happens.
We don't talk about collapsing a wave function.
That's of course what's going on, but no, let's not talk about that yet. Let's talk about the operational things that we might do to discover the laws of quantum mechanics, and then we'll put some words on them, such as collapse of the wave packet. Okay. So things are funny. In some average sense, the horizontal component of something is 0, but in each individual instance, you only get +1 or -1. Now, let's go a little further. Incidentally, the same thing would be true if instead of turning the detector this way, we turned it this way, so that the internal vector was pointing outward. It would still be true. Same thing. Okay, now let's do a little different experiment. Same setup to begin with, but instead of rotating the detector by 90 degrees, let's rotate it by 45 degrees. In fact, any angle. Let's not do 45 degrees. Let's rotate it by an arbitrary angle so that the internal detector orientation is now characterized by some angle theta relative to the vertical. So it's been rotated by angle theta, and do the same experiment now. We take the first qubit, subject it now to the detector oriented at angle theta. What do we get? +1 or -1. Do it again. What do we get? +1 or -1. What do we get? Do it again. +1 or -1. Never anything in between. But in this case, the average value of the experimental value of what comes out here is not equal to 0. It's equal to, what do you expect it to be equal to? Cosine of theta. Cosine of the angle. Exactly like the x component of a vector would be, or exactly like, yes, exactly like the component of this vector along the detector axis. The component of this vector along the detector axis would be smaller by amount cosine theta classically. Quantum mechanically, we simply get +1, -1, +1, +1, -1, plus, whatever, in such a way as to average to the cosine of the angle. As the detector gets more and more upright, cosine theta gets closer and closer to 1, and that just means it gets closer and closer to the value, to the answer if the detector were perfectly upright. Now and then you might get a minus sign, but mostly plus signs. And as soon as the detector gets perfectly right side up, all +1s. What about when the detector is almost upside down? Well, then you get mostly -1s, but here and there a few +1s. And so it seems that the average values of sigma are behaving as if sigma was the component of a vector. This is something, really different.
this is because you prepared these as ups. If you just took raw qubits, you get 50/50, you get 0, right? No, they just
If you
only-
took what?
The theta is only because you started with
Yes.
the ups.
Yes. Uh-huh. Yes, that's true.
Why do we need a collection of qubits?
Why do we need what?
A collection of qubits, since nothing is happening to the qubit, why can't you take the same one again and again?
No. If you take the same one and do it over and over again with the same detector, you'll just get the same answer over and over. You'll just confirm the previous measurement. So if you take one qubit, known to be up because you've made it, you know that it's up, and you subject it to this angularly distorted, angularly rotated experiment, you'll either get +1 or -1, but if you do it the second time, you'll just get the same answer you got the first time. You won't learn anything new. Incidentally, if that weren't the case, there would be no way to confirm that the answer that you got the first time was in any sense the right answer. The only way that you confirm that an answer is right is by checking it. And one way to check it is just, if I close my eyes and I look at you and I see you upright, and then I close my eyes again and look at you again, I've confirmed that the first time you were upright.
But the other one is also prepared in the same state.
Say it again?
The other one is also prepared in that state.
This one here? Second one? Yeah. What I'm saying is if you only have one of them, then you do the experiment, you either get +1 or -1, and then if you do the same experiment again on the same one over and over, you just get +1. But if you have a sequence of them and you do the experiment with a sequence of them, all having been prepared the same way, then you'll get a statistical distribution. Yeah.
So if you turn off the detector and turn it on again, will it still have a memory of the same unit?
Mm-hmm.
Switch it off, switch it
That's
on?
what I mean by measuring it again. Switch the detector off and do it and turn it back on.
So does the detector seem to store memory of?
The detector has an orientation to it, and when I say you
How does it
turn
know you changed or did not change the unit?
change the qubit. Say it again.
How does it know you changed or did not change the qubit?
No, it knows that it didn't change. That you didn't change the detector.
No, but you switch the qubit and now it's reset. But if you don't switch the qubit, it gives you the same reading.
Answer is it knows. No. It knows. It gives the same. There was only one qubit. You did the same.
Isn't it, I mean, the detector isn't remembering anything, it's just the qubit has changed.
I have a bunch of students in the audience. Some of them are sitting upside down. Some of them are sitting right side up. If I randomly open my eyes as a student, 50% is standing right side up or not. Close my eyes, look at another student, 50%, I don't know. But if I open my eyes and then close them, and then open them and close them and look at the same student, it's always the same way. How did my eyes know that the student was going to, that I wasn't looking at a different student? The answer is I just looked at the same student. Okay? So the whole thing is not that weird that we can't keep track and remember which of these things that we're looking at. Yeah.
So basically, we can think of it as the act of observing causes you to prepare that particular qubit.
Yeah.
So once you observe that one, you prepared it.
Yeah.
So now you're always going to get that answer.
Until you intervene by
Something else.
doing something else. That's right.
If you change qubits but leave the measuring apparatus in the same position,
Yeah.
you'll still get +1?
Okay, so let's see, what are we going to do now?
Well, you're not going to change the orientation of the measuring device, but you just measure a sequence of different qubits. Are they always going to be up, +1 or -1?
It depends. It depends on how they were prepared. Somebody might have given you a sequence of qubits which happened to be up, down, up, down, up, down, up, down. You might have gotten them from someplace. You got them from a, from a qubit store where they didn't have good quality control. But if all of these qubits were prepared the same way, and identical way, and then you send them through here, they will continue to be identical. Right. Okay, so what this is telling us is there's something funny about the notion of the state of a system. It's not as clear-cut and not as simple as the state of either a coin, which is either heads or tails, or a little vector, which has components in different directions. But, for example, when you measure the component along an axis perpendicular to the known direction of the vector, you get 0. Not so. So there's something intrinsically different, and the difference does trace to the big difference between the notion of a state in quantum mechanics and a state in classical mechanics.
At one point, you had here everything up +1. And then one by one you turned it, and some were +1 and some were -1. And that, each one you bring up, that which was -1, then becomes -1 back on the original.
If you do the experiment, say again.
If you bring one down, and let's say that it's -1 down here.
Okay.
Then you turn the apparatus up again, and now you said it will be -1 from now on.
No, not if you turn the apparatus.
If you turn,
Once you turn the apparatus.
if you turn the apparatus, I thought you said if you turn your apparatus up, that if it had measured minus when it was turned, that it would stay minus when you turn the apparatus up.
When you turn the apparatus, then you get a statistical distribution, okay, when you turn the apparatus. Once you have the qubit that comes out of this apparatus, let's say it was +1. Let's say it came out +1. And now you take that qubit over here and you turn the apparatus back up again. Then you're going to get a random plus or minus.
Then it'll be random when you turn it back up.
Yeah.
So in that way, then
Every time you turn it, it'll be random.
then with a random bunch of qubits.
You'll end up with a random bunch of qubits. Yeah. Yeah. Now, it depends on the angle. If the angle is not too large, if the angle is small, then mostly you'll get pluses. Right, mostly you'll get pluses.
You've postulated a two-state system and then a detector, but what would be the difference in logic in saying your signal was a variable because your detector is a two-state system, which seems like you get the same output.
Say it again.
You've postulated a two-state system, plus and minus 1.
Yes.
But then you have a detector that always produces plus and minus 1. If you postulated a variable to start with, your detector seems like it would still give you what you're...
The detector would still be what?
It seems like you're really saying your detector is a two-state system that you can orient, and it doesn't seem to imply that
Right.
state was...
No, you're absolutely right that at some point we have to come back to this and say the detector is a system and it has states, and understand the combined system as a quantum system composed out of two quantum systems. But let's not do that yet. Let's divide the world into detectors and systems, and then come back later and say, look, a detector really is a system, and we have to be able to describe it quantum mechanically also as a system, and to understand the entire thing as the interplay between two quantum systems. But that would take that will take some steps before we get there.
What if we change
What's the what?
What if we change the axis of rotation? Does it matter?
You mean if we rotate this way instead of? Yeah, no, it doesn't matter.
So, I mean, if we do one rotation in one using one axis and then the different axis.
Yeah. Right. You're right. You're right in guessing that the whole story is much more complex, but still, the story is more complex, but not inconsistent with what I said. So don't try to guess too far ahead. don't try to guess too far ahead. Let's take the simple version of it first, and then we'll eventually come to a much more rich understanding of it.
So for now, is it correct to think of the detector as something that could potentially return a continuous value from +1 to -1, but the system will only be, the qubit will only be in
now.
those two states?
For now, yes. Right. Right. If you like, you may think of, yes, for now, we may think of the detector as a thing which can be oriented in any direction, and when we measure it, it behaves like a classical system. Yeah. Eventually, we'll have to reconcile that with the idea that detectors themselves are quantum systems. And have to respect the same laws as the systems themselves. Okay. Okay, now I leave you with that to ponder now. And we're going to separate from this for a while and discuss mathematics. We're going to discuss the mathematics of the state space, or the space of states, of a quantum system. And as I said, it's not a set. It is not a set in the same sense that the set of configurations of a die is a set of 6 configurations. It's more complicated. All right, but we need some mathematics. We need some mathematics. We need some abstract mathematics. And the mathematics, as I said, is not the mathematics of set theory. It's the mathematics of vector spaces. Now, let's just discuss the word vector for a moment. You're familiar, of course, with the idea of a vector. A vector is an arrow pointing in a certain direction in ordinary space. And that's one concept of a vector. But there's a more abstract notion of a mathematical vector space. And mathematical vector spaces can encompass many, many kinds of mathematical objects, which are not necessarily pointers along an axis in space. I generally, when we get to this point, I generally make a new name, a non-conventional name that nobody else that I know of uses, for the notion of an ordinary vector in ordinary space. In other words, a thing pointing in ordinary space. I call it a pointer to distinguish it from the abstract mathematical concept of a vector. And we're going to talk now about the abstract mathematical concept of a vector. Don't think of it as pointing in 3-dimensional space, ordinary 3-dimensional space. We'll discuss in what space it points. All right, so let's talk about vector spaces. A vector space is a collection of mathematical objects, just like numbers are a collection of mathematical objects. And numbers, just the real number axis, for example, is a vector space. It's a special case of a vector space. It's a 1-dimensional vector space. Complex numbers are 2-dimensional vector spaces. All right, we're going to be talking about vector spaces of, for the moment, unknown dimensionality. And we're just going to write down a mathematical notation for an object in the vector space. And as I said, vector space is now just a name for a collection of mathematical objects. Completely abstract. A is a vector. And that's the notation for an abstract vector. It's Dirac's notation. And it consists of a vertical line, a crooked line, and a letter in between. And that stands for the vector A, whatever the vector A is. What can you do with vectors? Well, you can add them. I'm not going to tell you how to add them. I'm just going to tell you that given any 2 vectors, A and B, you can form their sum. And their sum is another vector. Let's call that other vector the vector C. So a vector space consists of a collection of objects which can be added. Numbers.
I'm sorry, I'm just confused. Vector versus vector space?
A vector space is a collection of vectors. Right. A vector space is a collection of vectors. the same distinction between number and numbers. The numbers are all the numbers. Number is a specific number. Okay. So as I said, numbers are a special case of this. You can add them. Okay. You can do something else with numbers. You can multiply them by other numbers. Well, eventually we will talk about multiplying vectors, but not yet. What we can do is multiply vectors by numbers, ordinary numbers or complex numbers, and we're going to be thinking about complex numbers. I hope everybody is comfortable with complex numbers. If not, you got to quickly get up to speed on complex numbers. But we don't need to know too much. You need to know that a complex number is a combination of a real number and an imaginary number, and how to multiply, add complex numbers, and you need the notion of complex conjugate. How many people here are familiar with the concept of complex conjugate? Most people, right? Almost everybody. So I'm not going to go in it now. But basically, for every complex number, there is another complex number with its complex conjugate. It's a mapping between numbers and their complex conjugates. That's an important notion. Keep it in mind, because it's going to come back. But for the moment, ordinary vectors, let's go back to pointers in space. Ordinary pointers, you can multiply by ordinary numbers, positive or negative. A pointer which is of a certain length in that direction, if you multiply it by 2, it's just twice as long in the same direction. Multiply it by -1, it just becomes in the same direction except in the opposite, in the opposite direction. So yes, you can multiply vectors by numbers, and in a complex vector space, we're now going to talk about complex vector spaces, you can multiply vectors by complex numbers. Now, do not try to picture this in your head as any kind of pointer in some direction. Just accept we're now talking about a mathematical abstraction where a vector, any given vector, can be multiplied by any complex number. I'm going to use, let's see, what shall I use for complex number? In my notes I used C, but I don't want to use C. Z. Z is a standard notation for, x plus iy is equal to z. So you can take any any vector, multiply it by any complex number, and it is still some, I'm not going to try to draw it for you. Stop trying to think about drawing vectors. If there is a vector and there's a complex number, you can multiply them, and it gives you some new vector. Let's call it, let's call it A prime. So you can multiply vectors by numbers, complex numbers. And that's about it. That's all there really is to a vector space. Any set of objects for which you can do this is a vector space. I'll give you some examples of vector spaces. If A's and B's are if A's and B's are just real numbers, then you can add them to make new real numbers. But you cannot multiply them by complex numbers and still expect to get real numbers. Okay? You can multiply them by real numbers and get other real numbers. So the real numbers are a real vector space. How about the complex numbers? Are the complex numbers a complex vector space? Yes. You can add them and get other complex numbers. Any two complex numbers you can add. And any complex number you can multiply by another complex number and get back a complex number. So the complex numbers are the simplest example of a complex vector space. Okay? Let me give you another example of a complex vector space. This one's incredibly complicated, but still pretty easy to write down. Take any function of a variable. Let's call it psi of x. Now, x may be an ordinary real variable. A function on a line. Function on a line, but it's a complex function on a line. It has a real and imaginary part. Complex function on a line. Can you add two functions and get another function? Certainly. So functions, just functions, are things you can add to get other functions. Can you multiply a complex function by a complex number and get a complex function? Yes. Take any complex function, multiply it by a complex number, you get another complex function. So functions form a vector space. Now that's a complicated idea, and I don't want to get that complicated yet. So let's erase that from the blackboard. I'll give you another vector space, another complex vector space. Let's just make some symbols. A bracket, and put in entries, two entries into the bracket. And the two entries are themselves complex numbers, alpha 1 and alpha 2. Alpha equals a complex number, both alpha 1 and alpha 2. And alpha 1 and alpha 2 can be anything. The collection of such symbols is also a complex vector space. Here's the rule. Supposing you have two of them, here's one and here's another one, beta 1, beta 2, and you add them. What does that mean? Definition. The definition of the sum of two, these are called columns. The sum of two columns like that is just to add the entries. Alpha 1 plus beta 1, alpha 2 plus beta 2. So given any two abstract symbols in which the entries are filled in with complex numbers, any two of them, alpha and beta, we can add them and get a third one. Okay. So column vectors like this, little columns of two entries like this, satisfy the first rule. And the second rule is that if you want to take a column and multiply it by a complex number, all you do is multiply each entry by the complex number. You multiply each entry separately, and then you construct something which is just z times that. So just pairs of complex numbers like this form a vector space. It's a very abstract concept, but not very hard. How about triples of them? Sure. Right. So any length of column like that. Now what you don't want to do is add a column of 2 to a column of 3. You don't have a rule for that. All right? So columns of different length form different vector spaces, completely different abstract vector spaces. Any question about the meaning, the abstract? And this is not hard, but it is abstract.
Are those the only two requirements for vector space?
Yeah, well, I think it's also important that there be a zero vector. Zero vector is the unique vector, which when you add it to any other vector gives back the same vector, right? I didn't feel like writing it down, but
closure requirement, the general closure requirement, the result be closed under
what?
a particular space.
Close under addition?
I think, right.
And close under multiplication by.
Which I think you've illustrated.
Yeah, 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 that's right.
Is this the same as matrices? Is this the same as matrices?
As a what?
Matrix.
Matrix. Yeah. This is usually the term matrices, in this class in any case, will be reserved for square matrices. Square matrices are collections of numbers which form square arrays, as many rows as columns. But the general notion of a matrix can have different numbers of rows and columns, and the vector would be a matrix with only one column, in this case 2 rows. So yes, this would be a special case of a matrix, but in many contexts one reserves the term matrix for a square matrix, and I will use it that way. I will use the term matrix to mean a square matrix. So I didn't want to use that terminology. Okay, are you thoroughly saturated with abstract mathematics? This should be straightforward for you. Okay, now we introduce another abstraction. Another abstraction. Basically, it's the abstraction of given a complex vector space, the complex conjugate of the vector space. The complex conjugate of the vector space is sort of the space of complex conjugate vectors. Just like you can have for any number a complex conjugate, any complex number, there's a complex conjugate to go with it. So in that sense, the complex number system has a dual version, which is the complex conjugates of the original numbers. So do the complex conjugate vector spaces. And roughly speaking, the complex conjugate vector space, or the dual vector space, usually called a dual, is roughly speaking the complex conjugates of the original vectors. We'll make that more precise as we go along. But what it is a separate vector space whose elements are in one-to-one correspondence with the elements of the original vector space. So if there is a vector A in the original space, let's write it this way, then there is a vector in the dual, it's called the dual vector space, but as I said, it is more or less the complex conjugate, and it's written this way. It's just written as a backward Dirac symbol. We'll learn to call these things bra vectors and these things ket vectors, but no, this is the ket vector, this is the bra vector, but for the moment, they're just symbols. An example, if the vector space is just the space of complex numbers, then the dual vector space is just the space of complex conjugates of those numbers. Okay, so there's a one-to-one correspondence between vectors and their complex conjugates. Let's write down first some postulates about the complex conjugate vector space, and then test it out by seeing if we can find a concrete representation of the notion. We'll write down some abstract postulates and then check, just as we did here. We said here's a concrete representation of the notions that we wrote down over here. Let's write down the abstract postulates about the dual vector space. All right. So first of all, for any vector, there is a dual vector. And they're in one-to-one correspondence. Next, if you take two vectors and you add them together, then the dual of the sum is just the sum of the duals. So if you take a vector which is made up out of the sum of two other vectors, then its reflection in the dual space is just the sum of the individual dual vectors. These are postulates. These are postulates, if you like, but they're not so obscure. The third assumption is that if you take any vector and multiply it by a complex conjugate, by a complex number, then its reflection in the dual space, now, anybody want to guess? Of course, it involves the dual vector to A, but not multiplication by Z, but multiplication by the complex conjugate of Z, Z star. Z star is the complex conjugate of Z. This would be true of complex numbers. If you take a complex number and multiply it by another complex number, then the complex conjugate of the whole thing is the product of complex conjugates. That's all this is saying. So we think of the dual vector space as basically just the complex conjugate vector space, in some sense. Okay, let's see if we can make any sense out of this in terms of these column vectors here.
Quick question.
Yeah.
Is A plus B the same as B plus A?
Yes, yes. A plus B is the same as B plus A. Good question. Yes, when you add vectors, and you can see that from here. I should have, all right, I'm sorry. Somebody asked me, are there any other rules about the definition of vector spaces? And indeed there are, among other ones, that may be all there is, that it doesn't matter which order you add them in. Yes. But you can see that here. The sum of two vectors is just given by numerically adding the complex numbers here. And of course, numerical addition of complex numbers doesn't matter which way you order them. Good. So that's a good point. Okay, so let's come back now to, let's put this up on top, and come back to this concrete, non-abstract representation of the complex vector space. Here we have a vector. This object is representing the vector A. The one that I erased with beta, that's representing the vector B. But right now I don't need the vector B. Okay. What about the object? If this object represents A, then what is the object which represents the dual vector, the corresponding dual vector? And the answer is, it's the same pair of numbers except they're complex conjugates. The same pair of numbers, not quite, they're complex conjugates, alpha 1 star and alpha 2 star. But just to keep track that we're talking about a different vector space, we write it in row form, not as a column, but as a row. This is just a trick to remember that this object belongs to the dual vector space, this object belongs to the original vector space, and that they're different. All right, so the dual vector space image of alpha 1 and alpha 2 is alpha 1 star, alpha 2 star. Okay. That's the dual vector. All right, now you can check with this definition are the postulates, namely that if you add two vectors and then take the dual, that whether or not you get the sum of the duals. And you can check whether when you multiply this by a complex number and then take its dual, whether it just multiplies by the complex conjugate number. The answer is yes. So just laying out a pair of complex numbers like this makes a vector space, and the dual vector space is the same pair of numbers except complex conjugated, and laid out in a row just to remember that it's not the same creature, doesn't live in the same space of things. And that's the idea of a complex vector space. As I said, again, very abstract and very easy. Final concept. Well, it's not the final concept, but the n plus first concept. I'm not sure what n is. How many people find this hard? It's not very hard. How many people find it familiar? quite a lot of people find it familiar. That's good. Those who don't find it familiar apparently didn't find it hard. That's also good. The product of two vectors. The inner product of two vectors. The inner product of two vectors, it's the analog of the dot product for pointers. The analog of the dot product for pointers. The inner product between two vectors is, strictly speaking, the inner product between a vector and the dual of a vector. Given two vectors, let's call them A and B. One does not form the product of A with B, the inner product. Instead, one takes B and constructs its image in the dual vector space, and then takes the product of the vector A with the dual vector B. In Dirac's language, you take a ket vector and you multiply it by a bra vector, and when you do so, you make a bra ket, or a bracket. Okay. The bracket. The bracket, of course, is this thing over here, and the two together. I think this one is called the ket, and this one is called the bra. So it's a bra ket. Right. So the inner product of two vectors is really a product of a vector and the dual of a vector. Now, is it the same as multiplying the bra vector A with the ket vector B? Question. Is it the same to multiply the bra B with the ket A or the bra A with the ket B? And the answer is no. The answer is no. It is not the same operation, but in fact they're closely related. The axiom, we're still talking about axioms now. The axiom is that these two are related by complex conjugation. I complex conjugated A to go from the ket vector to the bra vector. I complex conjugated B to go from the bra vector to the ket vector. So if this is the product of A, roughly speaking, times B star, this is the product of B star times A. This is the complex conjugate of this. So another postulate, another axiom of complex vector spaces is that the inner product of A with B is the complex conjugate of the inner product of B with A star.
So with that, I mean, in normal vector space language or whatever, nothing to do with quantum mechanics per se, I mean, there the inner product is just all the vectors are in the same vector space.
In an ordinary vector space.
Right.
Yes.
But so this is still called an inner product, even though it's kind of the special thing with the complex conjugate. So.
Yeah, well, the usual vector spaces that you think about are real vector spaces. And for a real vector space, for a real number, there's no difference between the number and its complex conjugate. So the real vector space satisfies the same postulates, except it's, the complex conjugation is completely a trivial operation.
But I mean, you could have a vector space where you take the inner product of two complex vectors and it doesn't involve any conjugation. You just multiply them component-wise and take the sum, right?
Yes, you could. You could invent such things. Then, of course, the inner product of a vector with itself would not be real. That's okay. Who cares? So you could invent such things. It turns out not to be terribly useful in the context of quantum mechanics. So, you know, it's largely a question of what's useful, and what's useful winds up being this concept. Right. But yes, you could certainly define such a thing. It's not a commonly defined thing. It doesn't seem to have a lot of use. This structure occurs over and over in all kinds of places, not only quantum mechanics. I mean, this complex vector spaces are very, very common things in mathematics. And okay, let's check now. Let's see if we can postulate a construction for the inner product of the dual vector beta. Remember, when you complex conjugate, when you take times the original vector alpha. This is supposed to be now, I guess I called it BA. And I haven't, I've written down the notation for B and the notation for A. Column vector for A, row vector for B, complex conjugated. All right. I will tell you now what the rule is. Again, we're making up rules which will satisfy those postulates up there. And it's a very simple construction. It's just beta 1 star times alpha 1 plus beta 2 star times alpha 2. In other words, you take the first entry of the dual vector times the first entry of the vector alpha, add it to the second entry times the second entry. So it's actually just a generalization of multiplying beta times alpha, but it's also a generalization of the dot product. If you remember about dot products of ordinary vectors, you simply take the sums of the products of the components. If you have two pointers and they're labeled by components, both of them, then the dot product is just the sums of the products of the components. Does that satisfy the rules up here? Where are the rules? I think I must have erased a rule, huh? I did erase a rule. The rule was
It's up there.
Where's the last one?
The last one.
I've lost it. Okay. What happens if you interchange alpha and beta, or A and B? Then this becomes alpha 1 star, alpha 2 star times beta 1, beta 2, if I interchange them, and that's equal to alpha 1 star, beta 1 plus alpha 2 star, beta 2, and that's just the complex conjugate of this. It really is the complex conjugate. So interchanging alpha and beta, or A and B, really does interchange the value of the product and its complex conjugate. That's the notion of a complex vector space and an inner product on the complex vector space. Now, let's just take a couple of special cases of inner products. What about the inner product of a vector with itself, or a vector with its image in the dual space? Let's take the inner product of A with A. What do I know about that? Well, first of all, let's I'm setting B equal to A. That tells me that the inner product of a vector with itself is equal to its own complex conjugate. I just substituted for B, A. The inner product of a vector with itself is equal to its own complex conjugate. What kind of number is equal to its own complex conjugate? A real number. So the inner product of a vector with itself is always real. That's pretty obvious just from here. If I take alpha and multiply it by its image, I get alpha star alpha plus alpha 2 star alpha 2. Each one of these is real. Not only is it real, it's also something else. Positive. Alpha star alpha, a number times its own complex conjugate, is always positive. So it's real and positive. The inner product of a vector with itself is real and positive, and it's considered to be the square of the length of the vector. The square root of the inner product of a vector with itself defines the length of the vector. So complex vectors have real lengths, real and positive lengths. Also, the square of both the square and the length itself are defined to be positive. So that's not too obscure. Every complex vector has a length which is the square root of the sums of the squares of its components, but squares now mean multiplied by complex conjugate. Next notion, important notion, the notion of orthogonality of vectors. The notion of orthogonality of vectors is, as we'll see, is a very important one. I'll give some examples in a few minutes. The notion of orthogonality between two vectors is exactly the same as it is for ordinary vectors, that the inner product, read dot product if you like, the inner product is 0. If the inner product of two vectors is 0, they are said to be orthogonal. That defines, or perpendicular. Okay, so two vectors are orthogonal if the inner product between them is 0. Let's see if we can make up some orthogonal vectors. It's very easy. Oh. What about if I take the inner product the opposite order? It's just a complex conjugate of 0, but the complex conjugate of 0 is 0. So saying that two vectors are orthogonal, it doesn't matter which order you put them in. The notion of orthogonality doesn't depend on order, although the general idea of inner product does. Right, so now we have the notion of orthogonal vectors. In a real vector space, how do you define the dimensionality of the real vector space? Well, give me a definition of the dimensionality. There are many definitions, of course, but anybody have one?
Number of entries in the vector. Number of entries in the vector.
Yeah, but let's work in a more abstract way without yes, that's of course correct, but the maximal number of orthogonal vectors that you can find in the space. Okay, so if the vector space is two-dimensional, ordinary two-dimensional vector space, there are two mutually orthogonal vectors. You cannot find a third vector which is orthogonal to both of them. Right? So the maximal number of mutually orthogonal vectors in 3 dimensions, I've got 3 mutually orthogonal vectors. Of course, there are many sets of 3 mutually orthogonal vectors, but given 3, I cannot find a 4th one. Right? So a 3-dimensional vector space has a maximal number of 3 mutually orthogonal vectors, and the same is true, or the same definition, its definition, is true for a complex vector space. The maximal number of orthogonal vectors that you can find is equal to the dimensionality of the space. It does correspond to the number of entries here, the number of components. It is the same, and you can prove that. It's a little exercise. Prove that the number of components of the vector is the same as the number of mutually orthogonal vectors. But are there any mutually orthogonal vectors we can write down? Sure, loads and loads of them. But a very simple case would be 1, 0. Now, 1 and 0, are 1 and 0 complex numbers? Well, yeah, real numbers are special cases of complex numbers. So a complex number can be real. Here's 1, and here's another one. 0, 1. This one has a 1 in the first place. It has a 0 in the first place. This one has a 0, and you get the idea. The inner product is 0 times 1 plus 1 times 0. Okay, so the two vectors, or let's just write it in terms of column vectors. 1, 0, and 0, 1. 1, 0, and 0, 1 are orthogonal vectors. The inner product of this one with the dual of this one is 0. Right? That's because 1 times 0 plus 0 times 1 is just 0. All right, so there are plenty of orthogonal vectors around, but in 2 dimensions, and this is 2 dimensions, once you've found 2 of them, you cannot find the third. So there's a little exercise. Prove that there can be no vector which is both orthogonal to this and orthogonal to that. That's not hard to do. It's very easy to do. Yeah. Yeah, 0, 0 is always orthogonal to everything, right? Yeah, yeah. Right, so one should be careful and say the maximal number of non-zero orthogonal, mutually orthogonal vectors. Good point, right? Okay, that's a mathematical interlude for tonight. Complex vector spaces. And the next time we will discuss how the space of states and what it means for the space of states of these simple qubits to be 2-dimensional vector spaces. Very, very different than saying that they consist of points in a set. The space of states is, in fact, a vector space. And then try to make contact with the mathematics of vector spaces and the strange things that are happening, or that seem to be happening here with these funny properties of measurements. That's where we want to go. So we've done some physics, some experimental physics on this blackboard up there, and we've done some abstract mathematics over here. And next time we want to connect them and show what the abstract mathematics, how it represents or how it can be used to represent this unusual kind of logic of qubits.
Looking strictly over patterns, is it going to be meaningful to define a multiplication operation where we create a 2 by 2 matrix, which would be beta 1 star alpha 1, beta 2 star alpha 1?
You're asking, yes. The answer is yes. Yes, absolutely. We'll construct inner products, outer products, all sorts of products. Yeah, yeah, that's right. The outer product of two vectors is a matrix. Yeah, yeah. And of course, how do you represent it? Well, the outer product of 2 vectors is represented this way. And it is a matrix, but we'll come to that.
All the postulates apply to a vector space of functions, for example, as well.
It does.
It's just less obvious than...
Yeah. A vector space of functions can be thought of as column vectors, but where the entries are continuous. So we have alpha. Alpha is the function, and alpha of the first entry, alpha of the second entry. Instead of that, we have a continuous family of alphas. Alpha evaluated at point x1, alpha evaluated at point x2, alpha evaluated at point x3. And of course, we can't really write it literally as a discrete collection like that. But if you like, think of these alphas here, alpha 1 and alpha 2, as just a function of 2 variables, a function of an entry 1 and 2. Instead of a function of x, it's a function of a variable which is either 1 or 2. So yes, complex functions form complex vector spaces. In the inner product, we will discuss that, right?
Back on the upper left board where you have that apparatus turned at angle theta.
Yeah.
If you consider the sequence of inputs going to outputs, the proportion of -1s to 1s would be given by cosine theta. Is there anything interesting about the distribution of the -1s within the 1s?
What does it mean?
Well, like higher order statistics maybe?
Still, what does it mean? Oh. They're just completely random. Completely random. Yeah, just a completely random variables. You're talking about the relationship between the different replications. And a whole bunch of spins, and you subject them all to the same. And the question is, I think you're asking whether there are correlations between them. No, they're completely independent, uncorrelated variables.
So still with the qubit experiment there, does it make sense to say that when you're measuring the qubit, you're affecting it, so you're actually preparing it in a new state?
Yes. That's exactly right.
That's why the first time does something, and the second time it just keeps it.
And that's a big difference between classical mechanics and quantum mechanics. In classical mechanics, you can measure something sufficiently gently to not affect it, to not disturb it. In quantum mechanics, whenever you measure something, you always disturb it. So this is an example of how measuring something disturbs it and puts it into a new state. And that's a good point, yes. Okay.
For more, please visit us at stanford.edu.